Hi, I'm Ben-Yaakov. This presentation is entitled The Nitty-Gritty of PWM Current Control Riddle. This is a riddle I've posted a LinkedIn discussion group that goes like that. Suppose we have a battery charger. This is the battery, this is the buck converter, V-in, the diode, inductor, and in order to control the current, we measure the current, compare it to the control signal of the current, and generate the PWM. Here are the pulses running the circuit. Now suppose I have a certain level of control signal here, like this, and there is a current. Now obviously for a buck converter we know that the duty cycle is the output voltage divided by the input voltage. D is V battery in this case over V in. So we have a certain current or a signal that is forcing a given current, and now we change this control signal to say higher level, for example, and obviously the current is supposed to go up and follow the control signal. Now the question is, what is really happening in the circuit that enables this current increase? Current will go from this level corresponding to this level to then to this level. Now battery voltage is the same. We don't assume that the voltage of the battery has been changed. Input is the same. So the duty cycle is the same. So what is going on here and what is really forcing the current to increase from one level to another level? So this was the question. So let's start with a very simple analysis of a basic buck converter in order to understand what's going on. So we have here a buck converter. This is again the inductor, diode. Here I have just a regular output section, a filter or capacitor, and this is the load. We have an input signal, input voltage, and this switcher or switch is running at a given duty cycle. Now we know that at steady state, and we are talking about steady state condition, the volt second during T on must be equal to the volt second during the T off, because the average voltage on the inductor has to be 0. So the volt second during T on is V in, here it is, V in minus V out times T on, and during T off it's V out over T off. So this can be rearranged in this way, and from this, since T on plus T off is the period, the switching period, we get V out over V in is T on over T, which is equal to duty cycle. Okay, so this is how we get this relationship between the gain or transfer ratio and the duty cycle. However, this is only an approximation. There are many parameters of the circuit that will affect the gain and which we have neglected them. So let's have a look at some of them, not all of them, but perhaps the most important one. And these are the resistance of the switch and resistance of the inductor. So these are included in the circuit, and obviously they will affect the transfer ratio between V in and V out. So we repeat now this volt second calculation, taking into account just these resistances. There are other elements, there's the ESR and other things that I'm not considering here. So during the T on, we have now the V in minus I over RS is a voltage drop here, and then there is a voltage drop here, and then V out. So this is during T on, and during T off we have V out, we have the voltage drop on the diode, which I'm not neglecting now, and the voltage drop on this resistance. This is during T off, and these should be or must be equal at steady state. Now, since T on over large T is D, T off over the period is 1 minus D, I can change this to here times D and 1 minus D. So this equation now can be solved for D, which I'm not doing, but obviously D will be now a function not only of V in of V out, but also function of the current. Okay, it is a function of the current. There is a current element here. So the actual duty cycle is related to the current. You can look at it in the following way, in a simplified, more intuitive way. You can say that the switcher, here it is, switch here, and I'm neglecting here now RS, let's forget about it, is producing an average voltage, which is V in times D. This is the average voltage due to the duty cycle operation of the switch. Now this voltage is equal to the battery voltage plus the voltage drop on the resistor. In this case, we have just the resistance of the inductor. So the duty cycle now times V in, or this voltage, has to overcome or to be equal to these two. So this is now, in very approximate way, intuitive way, is the equation that it's not, D is not V out over V in, but V out plus something. The plus something is this delta V, the voltage drop on this resistance. Or the current, I'm taking out now the current here, is now the duty cycle times V in minus V out, but divided by this KR. So if the circuit here gets a command to increase the current, it will increase a little bit the duty cycle such that the current will increase, the voltage drop on the resistance will increase to equal the new duty cycle times V in. So in the current mode control, what we have here is in fact a control, a very fine control of the duty cycle that is increased a little bit so as to move to another point with another current, with another voltage drop here, such that the new duty cycle again is equal times V in is equal to the total voltage drop on the circuit, and the voltage drop depend on the current. So this brings me to the end of this presentation. Thank you very much for your attention. I hope you found it interesting. Thank you very much.